Writing software is so much more than just telling a computer what to do. It's a craft, right? It's about building things, systems that are strong, efficient, and that actually make sense. And like with any craft, there's this endless journey, this quest for excellence, to find those core ideas that take your work from just good to truly great. So let's just get right to it. What is it? What's that secret ingredient? Is it just about being the fastest? Or being perfectly correct all the time? Or is there something more to it? Something about clarity, maybe simplicity? Today, we're going to try to find out. We're going on a little quest, and we've got 3 incredible books to be our guides, each one tackling this question from a completely different angle. Our first guide is an absolute classic, Java Concurrency in Practice. This book dives headfirst into one of the gnarliest problems in software, trying to manage a bunch of things happening all at once. The whole point is to give us the mental tools to build systems that aren't just fast, but are fundamentally correct, especially when things start getting messy and complex. Next up, we've got Effective Python. Now, this guide is all about the art of expression. It's not just about getting the code to work, it's about making it work in the clearest, simplest, most, Pythonic way possible. It's all about the idea that the best code is the code that's a breeze to read and understand. And for our third guide, we have DuckDB in action, which brings a really fresh, modern take on tooling. It shows us how picking the right tool can just completely change the game. It's about simplifying what used to be massively complex and unlocking some seriously amazing performance, all without the headache of those huge traditional data systems. All right, so with our guides at the ready, here's our game plan. We're going to see how the wisdom from these books helps us slay 3 of software's biggest dragons. First, taming complexity. Second, the constant need for more speed. And finally, how to write code that's actually built to last. And from all that, we'll pull out the universal principles that tie everything together. First up, complexity. From multiple threads all trying to change the same little piece of data to these massive, sprawling data models, every single developer is in this constant battle to just keep things from spiraling out of control. So how do we win that fight? Okay, one of the classic monsters hiding in the shadows of complexity is the race condition. And Java Concurrency in Practice has this perfect real-world analogy. Imagine you and a friend decide to meet at Starbucks, but you forget to say which one. So you check the one on Main Street. They're not there. You head to the one on Elm Street. But in that exact moment, they show up at the Main Street one. You completely miss each other. Whether you meet up or not depends entirely on the random, unpredictable timing of when you both check. That right there is a race condition. And this happens all the time because of a pattern that's super common. It's called check, then act. It's simple, right? First, you check a condition. Like, does this file exist? The answer's no. Okay. Second, you act on that information. Great, I'll create the file. But here's the flaw. In that tiny fraction of the second between your check and your act, some other process could swoop in and create that exact file. Now your action fails, the world changed right under your feet, and your initial observation is totally stale. So how do our guides tell us to handle this chaos? This is where it gets really interesting, because they have 2 completely different philosophies. On one hand, Java Concurrency in Practice teaches confinement. You basically lock your data up inside objects, and you strictly control who can get to it, limiting who can touch the state. But then you have DuckDB, which takes a path of just radical simplicity. By running inside your application, it just gets rid of entire categories of problems. There's no network, no separate server, no crazy configuration. It tames complexity by just limiting the number of places where the state can even exist in the first place. And this idea of correctness and managing complexity flows right into our next big challenge, performance. Because let's be real, it's not enough for our code to be right. It also has to be fast and efficient, especially when more and more people start using it. Effective Python gives us a perfect classic example of a performance trade-off. A list comprehension is, it's eager. It builds the entire list in memory, all at once. It's super fast, but if that list has, say, 1 billion items, you could literally run out of memory. On the flip side, a generator expression is lazy. It gives you 1 item at a time and only when you ask for it. It uses almost no memory, but the work is spread out. There's no single best choice here. It all depends on what you need to do. And you can't talk about Python performance without mentioning the elephant in the room, the GIL, or the Global Interpreter Lock. So here's the kicker. Even if you've got this beefy 16-core processor, the most common version of Python only lets 1 thread run Python code at any given time. This is a huge bottleneck for anything that's heavy on the CPU, and it totally changes how you have to approach parallelism in Python. All right, now for a complete 180 on performance, let's turn back to DuckDB. The claim from DuckDB in action is simple and honestly kind of staggering. It can query gigabytes of data in just seconds on your laptop. So how on earth is that possible? Well, it's a trifecta of really smart modern engineering. First, since it's in process, there's zero network delay. Second, it uses something called columnar storage. Think about a giant spreadsheet. If you only need to average one column out of 100, it only reads that one column, not the whole thing. And third, it uses vectorized execution. It processes data in big chunks, or vectors, which is way, way more efficient for today's CPUs. It's not magic, it's just performance by design. Okay, so our code is correct, and it's fast. We're done, right? Not so fast. The real test is, will anyone, and that includes you, 6 months from now, be able to understand it, fix it, or build on top of it? And that brings us to our third challenge, writing code that's truly built to last. Effective Python gives us advice that might sound basic, but it is absolutely fundamental. Document your code. A doc string isn't just some random comment. It's a contract. It tells other developers and future you what a piece of code is supposed to do, what it needs, and what it gives back. It's the first, most critical step toward making your code maintainable. Now, Java concurrency in practice gives us a more advanced pattern, but it's just as vital for maintainability, the open call. Basically, it means you should never ever make calls to code you don't control while you're holding on to a lock. Why? Because you have no clue what that other code might do. It could try to grab another lock, and suddenly you've got a deadlock, where two processes are stuck waiting on each other forever. It's an absolute nightmare of a bug to track down. And over in the data world, DuckDB in action shines a light on the power of common table expressions, or CTEs. Look, a really complex SQL query can become a completely unreadable mess of nested logic. The with clause lets you break all of that down into named, logical, step-by-step pieces. It transforms a tangled mess of a query into a clear, readable story. And that is absolutely essential if you want to maintain it long-term. Okay, so we've jumped from Java concurrency to Pythonic style to modern data tools. We've looked at all these different problems and different solutions, but if you kind of step back and squint, you start to see these universal principles bubbling to the surface. The very first principle is this: manage state, don't just share it. Whether it's Java's approach of locking state up inside objects or DuckDB's approach of just making the state radically simpler, the lesson is exactly the same. Uncontrolled, shared state is the root of almost all evil in software. It's where complexity and bugs come from. Great code is deliberate. It's disciplined about how it handles state. Second, understand your trade-offs. In software, there is almost never a single best way to do something. Is a Python list comprehension better than a generator? It depends. Is Java's strict locking system better than DuckDB's simpler model? It depends. Great developers don't just memorize patterns, they know when to use them. They get that they're always in a balancing act, memory versus CPU, or development speed versus long-term complexity. And finally, we come to what might be the most important principle of all: write for humans first. We forget this sometimes, but code has two audiences, computers and other people. And honestly, the computers part is easy. The hard part is making our code understandable to other human beings. This is the common thread, right? It connects Python's doc strings, Java's safe open call patterns, and DuckDB's readable CTEs. They're all techniques for communication. They're all about making our intentions crystal clear. So, in the end, this quest for great code, it's not just about being a technical wizard. It's about craftsmanship. It's about making deliberate choices to manage complexity, understanding the trade-offs you're making, and always communicating clearly. Because your code isn't just a list of instructions for a machine. It's a blueprint for the future. So what are you going to build with it?